Here's a fairly simple implicit function, y squared is equal to x to the third. We're going to see if we can find its first derivative, and then we're going to keep going and see if we can find its second derivative also. And we'll see some interesting algebraic techniques along the way. The calculus is pretty straightforward, but there's some interesting things we can do with the algebra to make sure that we end up with a simple, or as simple as possible, second derivative. And you may be surprised at actually how simple we end up making it. So if we start by looking for the first derivative, we're going to have 2y dy dx is equal to 3x squared. Taking derivatives on each side, remembering that when we take the derivative of something involving a y, we pick up a dy dx. We take a derivative involving something with an x with respect to x, we pick up a dx dx, or just 1. Solving for dy dx, in this case, by dividing on both sides by 2y, gives us dy dx is equal to 3x squared over 2y. Not too bad, and nothing we can really do to simplify that. That's pretty simple as it stands. If we keep going and consider d2y dx squared, we're going to need a quotient rule. So we take the derivative of the top, 6x, multiplied by 2y. We subtract the derivative of the bottom, 2 dy dx, times the top, which is 3x squared. We divide all of that by the bottom, which is 2y squared. So cleaning up some things a little bit here, we'll end up with 12xy minus 6x squared dy dx, all divided by 4y squared. Now, we don't need to leave a dy dx as part of our second derivative because we have a formula for dy dx. We can replace dy dx with something that involves only x and y's. So let's do that, giving us 12xy minus 6x squared times 3x squared over 2y, and all of that's going to be over 4y squared. And then we end up with a complex rational expression, a fraction in the top and a fraction in the bottom. So let's multiply the top and bottom of this by 2y so we can clear that out. So that's going to end up giving us 24xy squared minus, let's see, these two y's are going to cancel, so we're going to end up with 18x to the fourth. And that's all going to be divided in the bottom by 8y to the third power. Now each one of those terms has a 2 in it, so let's simplify that a little bit. Come up over here on the right, d2y over dx2 is equal to 12 xy squared minus 18 x to the fourth, all divided by, actually that should be 9, we're dividing the 2 out, all divided by 4 y to the third. Now, here's kind of an interesting little move. Our original function says that y squared and x to the third are the same thing. So any place I see a y squared at this point, I could replace those two y's with 3x's, that is x to the third. So I could rewrite this as 12x times x to the third minus 9x to the fourth, all divided by 4. I'm going to replace y squared, two of these y's, with x to the third, and leave the third y alone, because nothing happens to it. So we'll end up with 12x to the fourth minus 9x to the fourth divided by 4x to the third times y, which is 3x to the fourth over 4x to the third times y, and we can cancel a whole bunch of x's top to bottom. We'll end up with 3x over 4y, and that's it. So by doing some substitutions and then doing some good algebra along the way, we're able to write the second derivative, and actually it looks like it kind of ends up being even almost simpler in form than the first derivative was. Kind of interesting result. Not necessarily what we expect, and it has a lot to do with the form of the original function, y squared is equal to x to the third. Most things won't work out this way when you try to go to a second derivative with implicit derivatives, but this one's kind of designed to do this. And I like to show it to you so you can see a little bit of the algebraic techniques that are involved.